Hi everyone, welcome back to Chem Help ASAP. In this problem set video, we are going to be working buffer problems. Now, specifically, we're going to be working some simpler buffer problems that use the Henderson-Hasselbalch equation. Let's get started. Before we start our first problem, let's get the Henderson-Hasselbalch equation up on the screen. There it is right there. Also, on the right-hand side of the screen, I'm going to keep a very small table of weak acids and weak bases just for these problems. Okay, now let's read our first problem. It says, calculate the pH of a buffered solution of acetic acid and sodium acetate if the concentration of acetic acid is 0.15 molar and the concentration of sodium acetate is 0.28 molar. This problem is pretty straightforward, but before I jump into the math or plugging into the Henderson-Hasselbalch, let's just list out what we know. So we have acetic acid. We know its concentration is 0.15 molar. It is a weak acid, and its Ka is 1.8 times 10 to the negative fifth. Of course, I got that from my table of Kas right here. We also have sodium acetate in solution. Now, this is going to be our conjugate base. The acetate is the conjugate base. The sodium is really just a spectator ion. Its concentration is 0.28 molar. It always helps me when I'm doing these problems to organize my thoughts a little bit before I start plugging values into the Henderson-Hasselbalch equation. Okay, so I'm just going to recopy the Henderson-Hasselbalch equation down. There it is right there. Now I'm going to start plugging in what I know. Now I don't know the pH. Actually, that is what the problem has asked me for. However, I do know the Ka, and remember pKa is simply just negative log of the Ka value, so I just plugged in the Ka value there. Now, for our second term, we're going to have log of the conjugate base over the weak acid. We just listed our conjugate base above. It is the acetate. Our concentration is 0.28 molar. Our weak acid, we were given that concentration, it is 0.15 molar, so I'm just plugging those concentrations in. Now when I look at my equation, I see that it's going to be very simple to solve for the pH. I have one variable, everything else is plugged in. Now it's just working through the math. So first I'm simplifying the negative log of the Ka. Then I'm going to simplify my ratio of conjugate base to weak acid. Next I take the log of my second term, add these two together, and I get a pH of 5.01. Let's do another problem. How many grams of potassium nitrite need to be added to a 1 liter solution of 1.15 molar nitrous acid to create a buffer solution with a pH of 3.65? Again, I'm going to organize my thoughts here. I have nitrous acid in solution. This is definitely my weak acid, and I know the concentration is 1.15 molar. Again, I can pull my Ka value from my table. That is 4 times 10 to the negative fourth. I also have potassium nitrite in solution. That is going to be my conjugate base. However, I do not know the concentration of that solution. And I also know the final pH of my solution, and that is 3.65. Here again is Henderson-Hasselbalch. Let's plug in what we know. Okay, well, we know the final pH of our solution. That's great. We also know the Ka of our acid, so I'm just going to plug that in. Now, we don't know the concentration of our conjugate base. However, we do know the concentration of our weak acid. So I'm just going to leave the conjugate base in this term as just the concentration of A minus. Okay, let's do a little simplifying. Let's take the negative log of our Ka. Here you can see we get 3.4. Again, I'm going to combine like terms, so I simplify down to this. This is looking a little bit more like, okay, I can solve this equation. Now to deal with the log on the right-hand side of that equation, we're going to take the anti-log of both sides. So you can see I did that in the next step. Now 10 raised to the 0.25 is simply 1.78. Now we're looking like, okay, I can solve this. And I get a concentration for my conjugate base to be 2.05 molar. This is all well and good. However, my question asked me how many grams of potassium nitrite do I need to add to a 1 liter solution of this? So I still have a little bit more work to do. So if we remember that molarity is moles of solute over liters of solution, I know my molarity for my potassium nitrite is 2.05. I just figured that out. The problem also told me that I have 1 liter of solution. Thank goodness for putting ones in, right? So I can solve for my moles of solute, and that is really simple. That's still just 2.05 moles of potassium nitrite. Now it's a very easy matter. I just convert moles into grams, and I'm going to add 174.5 grams of potassium nitrite to this solution to create my buffer solution. Let's take a look at one more problem. This last problem reads, determine the Kb of ammonia. A solution of ammonia, 0.75 molar, and ammonium chloride, 1.4 molar, are mixed. The pH of the solution is 9. Just like in the other two problems, I'm going to collect what I know. I know that I have ammonia. That is a weak base. My concentration is 0.75. Now, yes, I can pull the Kb of ammonia. You can see it right here in my table, but the problem specifically asked me to calculate it. So the nice thing about this problem is I know what the right answer is. I just have to show that my Kb is 1.8 times 10 to the negative fifth. However, for now, I'm just going to keep it listed as unknown. Now, I also have ammonium chloride in the solution. Its concentration is 1.4. It is the conjugate acid of ammonia. So again, I have a weak base and a conjugate acid. And I also know that the pH of my final solution is 9. There are really 2 different ways to approach this problem, so I will show you both approaches, and you'll see that we are going to get the exact same answer. So always when you're doing these kind of problems, especially when you're working with math, don't worry about making your math look exactly like maybe my math looks. As long as you're getting the right answer, you're perfectly fine. Okay, option 1. For this option, I actually used the weak base form of Henderson-Hasselbalch. Now, this might be a form that you are not familiar with when using the Henderson-Hasselbalch equation. If that is the case, just wait until we get to option 2. Okay, so I know that my pOH is 5. And just as a quick side note, if you wondered where I got that number, remember that pH plus pOH is equal to 14. So that is where that 5 comes from. Now I am solving for my Kb, even though I already know it. I'm going to try to get the answer that is in my table. And then I'm going to do the log of my conjugate acid and my weak base. So I'm putting the concentration of ammonium chloride in the numerator and the concentration of ammonia in the denominator. Now I'm just going to simplify and solve for Kb. So first, I simplify my ratio, then I'm going to take the log, I'm going to combine like terms. Again, remember, whenever you have a lowercase p in front, it means the negative log. So I'm going to take the anti-log, and I get a Kb of 1.87 times 10 to the negative fifth, which you can see from my table is exactly what I should be getting. Okay, let's take a look at another way to do this. Option 2. You can see I kept the weak acid form of the Henderson-Hasselbalch. Now I need to plug in what I know. Okay, this one specifically tells me to plug in pH, so I plug in my 9 here. Again, I am going to gun for pKa, so I'm not going to put anything in there. And then I just need to put my concentrations in. Now here is where you need to be careful. Remember, your weak base or your conjugate base goes in the numerator. So this is where I'm putting my concentration of ammonia. Now, the conjugate acid of ammonia is the ammonium chloride. Actually, it's more just the ammonium, so that my concentration for that goes in the denominator. If you look back at my option 1, you can see that that ratio is flipped from the base form to the acid form. Okay, let's run through some math. Let's do some simplifying. So here we're going to simplify our ratio. I'm going to take the log of that. I'm going to combine like terms, and now I'm left with a pKa. However, ammonia is not an acid, it is a base, so I need to convert that into a pKb. Of course, just like pH and pOH, just remember that pKa plus pKb also equals 14. So that's a very easy conversion. Here I've converted it into a pKb, and then I just take the antilog and I get my kb value. And again, you can see it matches not only with my option 1, but it also matches with the value that's in the table. There are 3 different problems using Henderson-Hasselbalch. I hope you found this video helpful, and thanks so much for watching.